Today, I'll be presenting WARio, Efficient Code Generation for Intermittent Computing. This was a part of the 2022 International Conference for Programming Language Design and Implementation. To get started, let's talk about batteryless devices. Batteryless devices have been gaining popularity, particularly with the increase of IoT devices around the world. There are many environmental concerns surrounding battery disposal, and batteries are inconvenient to replace and can even be expensive at times. Batteryless devices address these concerns and have additional benefits like the ability to operate in accessible areas where it might be hard to change battery. Some examples of these sorts of batteryless devices are wireless sensors, medical implants, battery-free gaming devices, and even a battery-free phone. The picture on the slide there is a battery-free cell phone that was created by the University of Washington in 2017. Energy harvesting is closely related to batteryless devices. Energy harvesting is essentially energy that gets captured from the environment and converted into electric power. Energy sources are things such as thermal energy, light, vibration, heat, etc. The overall goal of energy harvesting is to make devices sustainable and be able to operate for what could potentially be an indefinite time period. Intermittent computing is also very closely related to this. So intermittent computing is essentially the goal to design systems to operate with an irregular power source. And this is very typical of harvested energy. A key component of this is to ensure that systems pick up where they left off in between power cycles. So in the graph there, you can see when the energy state is high enough, the system will turn on and continue computing or doing whatever it was intended to do. And then when the energy state is low, the system gets turned off. So as it seesaws between that, the system needs to be able to pick up where it left off so it can continue computing and ensure that the data stays intact. So, like I said, a major challenge is to maintain data integrity and computational progress and essentially be able to resume execution when power is lost. Non-volatile memory stores data persistently despite power loss, so that is something that is frequently used to do this. So one method is through checkpointing, which essentially saves the state of the program in non-volatile memory. These hardware checkpoints can be broken down into just-in-time checkpoints and statically placed checkpoints. Just-in-time checkpoints essentially save the registers just before the power fails, and it can be kind of difficult to predict exactly when the power will be lost. And statically placed checkpoints are placed typically by the compiler so that the state is always appropriately saved, and this is what WARio focuses on. And checkpointing like this, in general, can be somewhat inefficient, as you're saving all the information of the state of the program rather than just the information that is modified or needs to be saved. Another method of doing this is with software systems. So software systems can be manual or automatic. Manual adaptations of this require significant effort from developers. They frequently have to learn very specific languages and continuously adjust code based on the energy availability. And that's something that, like I said earlier, is really hard to predict. So that requires a lot of manual tuning. In contrast, automatic systems leverage compiler-based tools to place checkpoints based on code structure, and it significantly reduces labor required by developers. Overall, that kind of increases the system reliability. And even furthermore, you can break down software systems into code-oblivious systems and code-aware systems. So code-oblivious systems essentially checkpoint extra info into the non-volatile memory, similar to the hardware one where you're copying the data that you want to save as well as whatever other data there happens to be. So that ends up inducing a large overhead and can be pretty inefficient. On the other hand, code-aware systems, they checkpoint by inserting the checkpoint statically at compile time for specific regions of code. So by doing this, it only stores like the necessary registers, and that reduces the overhead and is a lot faster. Some of the intermittent computing software system goals that are specifically identified in this paper are that these software systems should be code aware. So like I said earlier, checkpoints should be placed where they're necessary at compile time, and that way it's able to make decisions based on the actual code. The software system should be automatic, so that way it can adapt to changes in energy conditions, and that is extremely important for unpredictable intermittent power supply. They should also be code transforming, which essentially means that they modify the code to enhance performance. So they might add code like these checkpoints to ensure data integrity and ensure that things pick up where they should. These software systems should also be compiler based. So that means that the optimizations are completed before the program is executed. So that way it's able to optimize based on the entirety of the program. Since the compiler is translating the high-level code to machine code, it can see the entirety of it, and so it's pretty transparent as to being able to optimize everything. Now, before we get into the actual design and implementation of WARio, a very key thing to understand is the write after read violations. So write after read violations essentially happen if power is interrupted after performing a read operation and a write operation on the same memory location, because then when the code is re-executed after gaining power again, it'll read in the newly written value and continue computing, which is incorrect. And more violations need to be handled to ensure that the data remains consistent and everything is as it should be throughout the program's execution. So this is an example of what a WAR violation might look like. Initially, the registers are empty, and the non-volatile variables of A and B are set to 4 and 2. And register 1 starts off with being set to the value of A, which is 4, and then A is set to the value of register 1 incremented by 1, so you end up with A being 5. And then you read in the value of B to register 2, and currently the value of B is 2, and then you increment it, and so register B ends up being 3. And so at the time that the device is powered off, the values of A and B are 5 and 3 respectively. And then when power is restored, the code's going to be re-executed again. So register 1 is going to read in that value from A, which is now 5, and then add 1 to it, get 6, and then register 2 will read in that value from B, so 3, and then you add 1 to it, 4, and then you've essentially re-executed the code an additional time, and you end up with A being 6 and B being 4, whereas it would have been corrected if it ended up with A as 5 and B as 3. So the way to resolve this is by placing a checkpoint between the read and write instructions. So the current state-of-the-art approach, Ratchet, does this. It's automatically added at compile time, but this can induce high overhead since there's no way of restricting the number of checkpoints that might be added. So if you have code with many WAR violations and consecutive, lots of them, especially code with loops and things like that, it can really significantly increase the overhead. So WARio stands for Write After Read Intermittent Computing Optimizer, and so this essentially optimizes the state-of-the-art approach that we saw previously. So in a code region with consecutive WAR violations, the write operations are clustered and moved to be later. So as you can see in the optimized code here, you set the registers to A and B prior to checkpointing, and then you do the write operations. And by doing this, instead of having 2 checkpoints, you end up with 1 checkpoint. And it is beneficial and conserves energy, improves execution speed, and reduces overhead. This is particularly effective in loops, and the more consecutive and unrelated war operations there are in the code, the more it can benefit from this reordering and clustering. Moving on to the system design, WARio was designed following the intermittent computing system goals that we discussed earlier. And a few of the specific features that we're about to discuss address those goals. So first of all, WARio supports C programs, so it turns regular C code into a war-protected executable using a series of passes that we'll talk about a little bit more in depth in a second here. But since WARio is designed to work with embedded C, it's very widely applicable. Also, previously we discussed the difficulty of deploying batteryless energy harvesting devices in environments where the power supply may be inconsistent, but WARio bypasses this challenge by applying the war preventative optimizations without requiring prior knowledge of the environment or the energy supply. WARio is also able to ensure that forward progress is made even in extremely low power devices or low power environments. By optimizing the checkpointing process, the frequency of checkpoints is reduced, and that ends up decreasing the energy required to perform the checkpointing, and so forward progress is always able to be made. And again, no programmer involvement. A developer doesn't need to restructure the program manually or resolve any war dependencies. Like we talked about, automatic is one of the big goals for a system like this, but WARio doesn't require any manual modifications by the programmer. And lastly, WARio is able to ensure no war violations occur from interrupts. So interrupts are common in embedded systems, and they can sometimes cause war violations. But WARio ensures that there are no interrupt-induced war violations by checkpointing stack data and carefully managing the stack pointer. And we'll talk about this a little bit more when we get deeper into the actual implementation. Also, WARio focuses on single processor embedded systems with direct physical memory access and register access and non-volatile main memory. So now let's get a little bit more into the architecture and a little bit more into the implementation of WARio. So essentially, WARio extends the LLVM compiler primarily through middle end and back end transformations. Does a little bit of front end, but it's pretty standard, and we'll go more in depth into each of these. So the front end transformations, they're pretty standard, but the C code is transformed into a LLVM intermediate representation, the IR, which is shown on the slide here, simple hello world program, and then to the right, that is the IR from LLVM, so you can see that it has a lot more details about the program. And then the IR files are created for each individual C file, and they're merged into a single IR for the whole project. And this detailed information is used for optimization, but like I said, it's pretty standard front-end compiler transformations. So the bulk of the work for WARio, it happens during the middle-end transformations. So the main tasks of the middle end are the loop right cluster, the expander, the right cluster, and the PDG checkpoint inserter. So the loop right cluster we'll discuss in depth here in a minute, but its purpose is to reduce the number of checkpoints in a loop containing multiple war violations. The expander does a lot more function inlining than usual, and since the calls are replaced by the actual function code, the need to add a checkpoint due to a function call is eliminated, so that helps reduce the number of checkpoints that are required. And the right cluster is really similar to the loop cluster. Same goal, to reduce the number of checkpoints for clustered war violations. It's just a little bit simpler and slightly less aggressive. And the PDG checkpoint inserter inserts checkpoints to break the remaining WAR violations that the optimization does not address. Now let's get into a little bit more detail about the loop right cluster. So on the slide, it's got the simplified sort of explanation of each of the steps, but don't need to look too deep into that. But the algorithm starts by identifying loops that are candidates for clustering. So these requirements are that the loop needs to have at least one WAR violation and it needs to have no function calls. And once the candidates are identified, they're unrolled n times, where n is the unroll factor. So in this example, it's 3 times. So you can see iteration 1, 2, and 3 in the step 1 under unroll loop. And we'll discuss more about determining the optimal value for n later during the evaluation. After unrolling, the WAR rights are moved to the end of the unrolled block to limit the number of checkpoints that are required. And to ensure that all of the WAR rights are completed, even in the event of an early exit, the algorithm adds writebacks to all of the exit points. So that happens in the modifying early exits. And then if the read part of the WAR has a potential to depend on a postponed write, the dependent read handling component of the algorithm will stop the write from being rescheduled. Or it could insert a runtime check to ensure that the correct value is read from memory. So the runtime check doesn't really increase overhead significantly, especially when compared to checkpointing. But yeah, so that is each of the components that make up the loop right cluster. And like I said, the regular cluster is slightly simpler. It doesn't have the runtime checks and doesn't do the stopping a write from being rescheduled, just because that's not necessary outside of the loop scenario. So now we're going to move on to the back-end transformations. So the 3 main things here are the stack spell checkpoint inserter, the idempotent stack pop converter, and the epilogue optimizer. Like you can see in the image, the stack pop converter and the stack spell checkpoint inserter are existing transformations, but the idea of using a hitting set and the epilogue optimizer are things that are unique to WARio's implementation. So the hitting set stack spell checkpoint inserter addresses stack spills, and these can occur during the register allocation process if there are no more empty registers, and so the registers end up spilling onto the stack. So the way this is implemented is that the LVM register allocation disallows the reuse of stack slots. There's a compiler option that's specified to ensure that. And that way the remaining stack spills are only a possible WAR violation if they're in a loop and that loop re-executes a basic block. So the goal of using the hitting set for the checkpoint inserter is to determine the minimal number of checkpoint locations to cover the stack spills. So that way you're reducing the number of checkpoints overall and just reducing the energy and overhead required. So then the idempotent stack pop converter ensures that the actions involved in a stack pop instruction can be repeated without introducing a WAR violation. So during a stack pop, the stack variables are read into registers and the stack pointer is adjusted. So the idea of the converter here is that by adding a checkpoint between reading the data into registers and adjusting the stack pointer, it's able to ensure that there's no WAR violation. So the third transformation is the epilogue optimizer. So it basically optimizes function epilogues to minimize the need for additional checkpoints at function exits. So function epilogues basically just free the allocated space on the stack, returns the control flow, and sets everything back to its initial state, sort of in response to the function prologue. But yeah, so it basically just reduces the number of checkpoints that might be required at function exits by making the epilogue more efficient and optimizing it. Moving on to evaluation, first we'll take a look at the unroll factor selection. So the unrolled factor was introduced earlier with the loop right cluster for the middle end transformation. So n is essentially how many times you unroll the loop, and it's a key part of efficient loop execution. So this graph here, the top one is checkpoints, bottom one's overhead, and the x-axis is the unroll factor of n. So you can see that as n increases, the checkpoints decrease, which is ideal. That's what we're looking for. But then when you take a look at the overhead, initially it decreases, but then there's a potential for it to increase as n gets larger and larger. So the optimal value of n for these particular benchmarks was set to be 8. So for the results gathered from these benchmarks, n was set to 8. So moving on to the result, WARio was evaluated using processor emulation, and it's a common method of assessment for any work that involves intermittently powered devices. So the evaluation relied on information collected from the emulator, and that included things like the number of checkpoints, clock cycles, location of checkpoints, etc. So the software benchmarks that were used in this evaluation were CoreMark, a couple of programs from the MeBench suite, and TinyAES and PicoJPEG, both of which represent real-world libraries. All the benchmarks were compiled with WARio from plain C code. In the results graphs here, the blue dashed line is the complete implementation of WARio, and the gray dotted line is Ratchet. So compared to Ratchet, the average execution time for all benchmarks with WARio was reduced by about 45%. And WARio with Expander reduced the average overhead by up to 58% compared to Ratchet. So specifically, you can see the compiler transformations, the epilogue optimizer, the right cluster, the loop right cluster, and how each benchmark benefits differently from these optimizations. Dijkstra has very low execution time overall, just because there were not many WAR violations. But overall, the experimental results show that WARio's optimizations are able to consistently reduce checkpoint overhead when compared to existing state-of-the-art methods like Ratchet. In conclusion, WARio's compiler-based optimizations are able to reduce the number of required checkpoints, which in turn reduces the checkpoint overhead. This enhances the overall efficiency of intermittently powered devices and is able to address some of the challenges faced in energy harvesting technology. Thank you.